Good day, everybody. Welcome to the IEA Greenhouse Gas R&D Programme's 9th webinar in our series. My name is Tim Dixon, the Technical Programme Manager. Our webinar today is on fault zone permeability and its importance to CO2 storage, and it's going to be given by James Craig. But just to mention quickly an introduction to ourselves, that we, IEA Greenhouse Gas R&D Programme, known as IEA GHG, we need to go back one slide actually. We are part of the International Energy Agency Energy Technology Network. We exist because of our members, 32 members from 18 countries, plus OPEC, EU and CIAB, and companies and other sponsors in that, those members as well. And what's important for us is that our members, and for our members, is that they set our technical program and the work that we do. And we are a technically based organisation. We don't stray into the world of policy in terms of being policy prescriptive, and we don't advocate any one particular technology. But having said that, the main focus of our work is carbon dioxide capture and storage. So our work, we focus on R&D, on technologies to reduce greenhouse gas emissions from the use of fossil fuels, and the main technology there is carbon dioxide capture and geological storage. And we commission studies, we undertake workshops, we run the main conference series GHGT, which is in November, and we keep our members up to date with developments on all aspects of carbon dioxide capture and storage. As part of that, in commissioning studies, it does give us a wider view on aspects, and we tend to bring things together, several projects or studies into topics for webinars, which is what we're doing today. In front of you, you can see our members, 32 members, which we're very pleased to have, and the organisations at the bottom are organisations or examples of organisations where we are active, because it's very important with technology R&D that the reports are then used in practice. And we are active in the UNFCCC. For example, we're very pleased to be involved in the main CCS side event at COP22 in Marrakesh, which will be on the 8th of November. We're active in the Carbon Sequestration Leadership Forum. We're active in the International Maritime Organization, who runs the London Convention meetings as well. So today, the technical part of the webinar will be presented by Dr. James Craig. James is our senior geologist, and he looks after all aspects really of the storage side of our technical program. That includes the studies and projects that we commission and manage, and also our networks, monitoring network, modelling network, risk management and environmental research. Prior to IEA GHG, James worked on R&D programs for UK government on renewable energy and other low carbon technologies, including geothermal. And before that, he came from the oil industry with wellsite operations and other consultancy work then. So with that, now I'll hand over to James to talk to us about fault zone permeability. Thank you, James.
Right, thanks for that introduction, Tim. As Tim said, we are particularly interested in fault zone permeability, and as we are do a lot of, I would say, generic research into CO2 storage, particularly of interest for our members, but also for a wider audience. We've commissioned two separate studies, the first being on how CO2 might affect fault stability, and a more recent study on fault permeability, looking at general properties of faults and how they pertain to CO2 storage. So today I'd like to run through the significance of fault permeability, relevant properties of faults, the factors affecting hydraulic conductivity, geomechanics, and a little bit on natural CO2 seeps leak mitigation, and then summarizing today's topics. So, why are faults important? Well, for the first very obvious point, and appreciate that many of you will have a very detailed knowledge of this subject and others less so, but important to recognize that faults are a widespread geological phenomenon in all kinds of rock formations. It is well known that they can act as natural conduits for fluid seepages, not just oil and gas, but also water. But it's also well known from the oil industry that they can have sealing properties and can lead to raise reservoir pressures, and the Snøhvit field is a very good example of that. So they do need to be understood. Just a quick revision as to why they form. Within the Earth's crust, general tectonic movement, we are a dynamic planet, and crustal plates move around, and also sedimentary basins continue to expand, develop, and create large thicknesses of sediment, which creates stress in the crust. And depending on the orientation of maximum stress, shown here as sigma 1, and minimum stress sigma 3, faults will form in different orientations. And those can be plotted, as you see in stereo plots, to the right of this diagram. So, faults are often exposed in terrestrial, particularly road cuts are a very good place to see them. Dislocation is fairly obvious, and in different rock types the style of deformation does vary. On the right you see brittle deformation in sandstone, which is largely comprised of resistant minerals like quartz, feldspar, which when crushed form what is known as a cataclastic crushed mineral gouge. On the left you see something more typical of a clay-rich shale formation. Here they have platy clay minerals which tend to form in a more plastic, ductile fashion. I would caution a little bit on shales. I want to come back to this topic later on, because they can also become and deform brittly under certain circumstances. So this effect of blocks of rocks crushing each other leads to a crushing fault zone, but within the core there will be a gouge of fine minerals, on either side of which can be quite extensive what are called damage zones of fractures. And quite often these can be mineralized, as you can see on the right, where there are voids opening and conduits of fluid have clearly influenced formations, and this is a common phenomenon. What is also fairly clearly evident is the degree of permeability across the core and the damage zone, and as you can see this can vary by up to 4 or 5 orders of magnitude. The other point about faults is that the crushing and central core weakens the formation, thereby forming a plane of discontinuity and slip, and of course that natural slip occurs all the time on faults, often to very minor degrees, but on continental or even subcontinental scale these can be felt and can be quite significant. So we need to recognize that faults may not necessarily be one simple damage zone and core, but they may be multiple cores. And the significance of this, it can reduce the tensile strength of the rock formation, which can and does have an influence on not just the degree of permeability, but also the hydraulic conductivity. So, fault complexes are, as I said, are highly heterogeneous. They branch, so we can get anastomizing, in other words, channels of varying degrees of fractures, and indeed gouge material, that is the fine mineral material in the core of the fault. So it's clear they're highly anisotropic, very highly variable permeability, and indeed in situ permeability measurements are supported by numerical models which show highly nonlinear behavior. This is hardly surprising if we're talking about different rock formations, which I alluded to earlier on. And crucially, they're highly sensitive to changes in effective stress, and I want to come back to this a little later. So, I mentioned the dynamic nature of our planet. Well, of course, what happens is, particularly talking about sedimentary basins, which is where oil and gas come from, but are also the prime targets for CO2 storage sites. As integrated or in stratigraphic successions of potential reservoir and caprocks form, they're buried, compacted, and as a generalization, doesn't necessarily, can't take it as a rule of thumb, but as a generalization, with increasing depth of burial, so compaction reduces permeability. And in fact, in the case of clays, there are some circumstances where compaction, and then maybe inverse, where the formation is not just buried but then uplifted, can cause a change from ductile to brittle deformation, leading to the formation of vertical fractures. So we also need to recognize, that's talking about permeability. So now I'm slightly changing the emphasis on how fluid migration or the important factors that relate to fluid migration need to be taken into account. This, although the title of the slide is CO2 migration, it also pertains to any fluid within a rock formation. Because what happens is, as the fluid migrates, the capillary pressure, if you like, that is the pressure exerted by different fluids as they move through a porous medium, controls the rate at which they transit or move across a barrier. Now, as far as CO2 is concerned, that CO2 will only migrate if there is a balance between the, if you like, the accumulation of CO2 on one side of the barrier, for sake of argument, we could say a fault here, and the other side. And when it reaches a point where there is a balance between the fluid pressures on either side, it will migrate. But of course, this is happening at a nanoscale, so the diameter of the pores is a key factor in the migration rate, and indeed whether that particular fluid migrates across a given barrier. Now, earlier on I mentioned the formation of gouge material, so you can see that the greater the amount of micropores, say, caused by accumulation of clay, then this will affect the migration of the CO2. So this will influence, if you like, the lateral migration of a fluid. But we need to think about, having moved across that barrier, then what happens, what are the influences on hydraulic conductivity once it's crossed that barrier. I've mentioned the clay content of a formation, not necessarily a fault, but in this case that's what we're talking about. The influence of the depth of burial, and now crucially the stress regime acting on that fault, because what happens with, after say horizontal migration, fluid accumulation may then give rise to vertical migration. But what is crucial here is the extent of the stress regime acting on the fault, and indeed the strength of that fault. The composition of the fluid will also be a factor in fluid migration, because of the, if you like, the size of the molecules that are migrating through the pores in the rock. So, stress regime is, this is a fairly, it's a standard approach to assessing stress in a rock formation. That is, if you like, normal stress, which is the horizontal axis, and the shear stress, TOR, which is the vertical axis. If the formation is normally stressed, then and stable, then it stays within inside a stability envelope. But if there is a change, possibly due to an increase in fluid pressure, that, if you like, that stress envelope shifts to the left, and once it reaches the failure envelope, then shear can take place. Now this has two implications. One, it could lead to a dislocation, minor movement along a fault, depending on the level of stress already in the system, but also it might affect conductivity as the stress acting on a vertical fault plane, as that stress is varied, or the natural stress regime that occurs, if it's in a critical stress condition, then conductivity could well occur, whereas if the opposite is true, then the fault should be sealing. So we're now talking about the possibility of fault reactivation, and this is possibly influenced by affecting what's known as the friction coefficient. In other words, the ability of different rock types to resist stress-induced movement. That depends on the type of rock, and there is a variation in the friction coefficient which can be reduced, particularly if clay minerals are present. So clay minerals can act as a sealant, but they can also reduce friction along a fault. Fluid content may also affect the friction coefficient, and this is an attempt to experimentally try and evaluate the degree to which the friction coefficient could be affected by CO2. Now I must stress here, this is an experimental condition. So the limited evidence, and it is limited evidence, is that if you expose CO2, in this case to a carbonate mineral, it will reduce the friction coefficient at a higher temperature. I would emphasize though that this is based on fairly limited evidence, and The extent to which this might influence fault reactivation is unclear. You will recall at the beginning of the talk I showed an example of a fracture system in a damage zone. It's very well known that mineralization occurs in faults and damage zones. They act as natural conduits. Depending on the type of mineralization, and this is natural mineralization, so it's not something that's happening now, it's something that happened in the past. But the degree of mineralization will determine the degree of fracturing that could occur on stress-induced faults. So another factor to be taken into consideration. So in terms of trying to predict how faults might behave, geomechanical modeling is applied. That is, modeling the way rock formations might behave under varying degrees of stress. And this can look at slip tendency, fracture stability, and dilation tendency. And although there is quite a lot of work that's been done on this, the extent of published material is not widely. I'm not saying it isn't available, but it's not that widely available. But just to show you an example of some work that is directly pertinent to CO2 storage is this example from the Caprock gas field, which was part of the insular storage site in Algeria. Now what happened here is that there was this is a natural gas field with naturally occurring CO2 that was re-injected into a reservoir. As this was a relatively new site, it was very well monitored, and it became evident that there was some stress-induced dilation in a fracture. What was also done here was some microseismic monitoring, which allowed the operators to detect the pattern of stress developing and dilation. There isn't time today to go into this example in detail, but it's maybe something we can come back to at a later time. The other point I would make is it did present an opportunity to model geomechanical movement, and what this slide shows is that a reasonably good match was achieved given the opportunity to monitor how the reservoir behaved. Another point to point out on this particular example is that with accurate satellite measurements, it was possible to link this to a very slight, and I mean millimeters, rise in the ground immediately above the particular part of the reservoir where the CO2 was being stored. I'm going to mention natural CO2 seeps for two reasons. They are widely studied and they are a widespread phenomenon, so we shouldn't be surprised or even necessarily worried that large amounts of CO2 in very specific areas are emitted by quite natural processes. And the reason they're studied is it gives a very good opportunity to measure fluid flow along faults and fractures. And you can see on the right the submarine example of a very high level of emission, and a terrestrial example where very low levels of CO2 are emitted, but there is sufficient concentration here to affect the vegetation. There is one very important message to take home from this though. These are natural seeps. These rates you would not expect to see these rates from a fault close to a CO2 storage site. They offer a good opportunity for natural research and linking faults to CO2, but these rates are not what you'd expect, or would you never see this coming from a planned CO2 storage site. Mitigation measures have been considered for fault leakage. This is part of a wider, if you like, appraisal of CO2 storage, and different methods have been proposed, and in certain cases some field experimentation has taken place. The first point, of course, there is back production of CO2. That is always possible, and then I believe there is some work done at the Ketzin site in Germany to measure what happens during back production. There are hydraulic barriers. That effectively is pumping saline in, say, above a plume to suppress its advance. Now I must stress here that the example you see on the right is purely theoretical. This is a hypothetical example. It's an EU-funded project which was done to model how effective this type of system might be. At a far more lower reduced scale, there's the concept of using biofilms, that is, I believe the bacterially induced formations which quite literally block pores and prevent the release of gas, and indeed microbially induced calcite precipitation, which has been field tested, but we're not talking about at great depth. This is an entirely experimental type of approach. An inorganic approach is to use reactive grout, which is reactive to CO2, effectively forming a cement. It's also worth mentioning that reservoir depletion could be another method. Now, there is a very good example off the coast of California of a hydrocarbon reservoir where there are known natural seeps from the seabed, in fact one from faults and other fractures. The reservoir that's related to these seepages has been producing oil for a number of years, and over a decadal scale those seepages have declined, they've reduced, and that's a direct result of production from a reservoir. And what that does is increases the effective stress and effectively slows down the natural seepage. So I think we can conclude that fault zones are highly complex, they are highly varied, permeabilities vary over relatively short areas, over 4 to 5, and are quite dramatic in terms of magnitude. Faults can be hydraulically conductive and sealing, and can be present in a single region, and therefore understanding burial history is an important consideration when considering, if you like, the hydraulic properties of faults. Fault permeability is sensitive to effective stress, particularly stress acting normal to a fault plane, and can be influenced by reservoir pressures. It's worth pointing out that vertical conductivity along fault planes is perhaps one of the strongest influences is the effective stress, but also the tensile stress of the rock. And as you've known earlier on, I showed that you can have extensive fracture zones, so that can influence the potential conductivity of faults. So one of the predictability of hydraulic conductivity, bearing in mind the stress field, also depends on the orientation of the fault to that stress, and indeed to the extent of any mineralization that has taken place. Detailed fault studies and in-situ permeability measurements are supported by numerical models, and these show highly nonlinear behavior and flow. And a point I perhaps didn't mention is that transient high permeability may be caused by high fluid pressures, and that can lead to episodic fluid flow. Finally, I think it's worth stressing that in terms of planning CO2 storage sites, site-specific petrophysical properties of faults, that is the permeability, stress, possibly fluid conductivity, mineral content, are valuable to gain an understanding of their response to elevated pressures. But it should be stressed there is widespread experience of working with faults and fractures, and providing you have a sufficient understanding of their properties, it shouldn't necessarily restrict storage development. And in fact, there are storage sites where faults are present, and so we should bear that in mind. Obviously, they need to be carefully characterized to ensure that they don't become conductive or are potentially conductive, and it goes without saying that you need an effective management and monitoring plan so that you can understand how the fault or faults might behave once sites are used for CO2 storage. And I would be very happy. Oh, sorry, a few. Just to say that future directions of research, I think, are geared towards looking at numerical models, understanding magnitude and uncertainties of fault orientation and other heterogeneities linked to geomechanical interpretations. So in other words, building on existing knowledge, and a proposal to produce guidelines for risk assessment specifically dedicated to the treatment of faults in CO2 storage projects. Oh, gone too far. I would be very happy there to take any questions you may have.
Okay, thank you very much, James. We've got a few questions coming in, so please write your questions in and we'll try and deal with those. First question in, James, is on the risks of earthquakes by drilling near faults. It's a question, I think, prompted by occurrences in Oklahoma.
Yes. Well, a couple of things, general points to say, because this is pertinent to a number of different industries, not just CO2 storage. I think the questioner refers to brine disposal, particularly in Oklahoma. The term earthquake is used quite widely, but I think we have to be a little bit careful here, because earthquakes depend on, if we're talking about felt events, then these might not be major earthquakes. As I showed earlier on in the case study, seismicity will always occur during injection of fluids, but we need to be careful about this terminology because the seismicity may be at very low levels and certainly only detectable by sensitive instruments. So to induce something of greater magnitude, you would need to inject very large volumes of fluid. And the other point to make on this, it very much depends, as in case of fracking examples, on how the stress conditions of fault. So you can't automatically say that you will cause seismicity by injection. One final point, and this is pertinent to the United States, is that brine disposal in Oklahoma is generally done at stratigraphic levels that are close to what geologists refer to as basement. These are very ancient rocks of crystalline basement beneath the very large sedimentary sequences above certainly the sort of central strip of the continental United States. So geological conditions play a very strong role on the level of seismicity as well as the quantity of fluid that's injected.
Okay, we've had several questions, James, on actually asking for, are there relevant publications or any good recommendations for publications or studies on both fault reactivation in reservoirs and on permeability measurements in data, so citations or reports?
Well, the short answer to that is our report will be published fairly.
Yeah, we have two reports.
We have two reports, but the one that's probably most relevant to this will be published fairly shortly. As far as permeability measurements are concerned, I would need to investigate relevant citations on that. I would say that both these reports that one is published now, and it's called Criteria of Fault Geomechanical Stability During a Pressure Build-Up, 2015-04, and the one that will be published soon is called Fault Permeability. There are several citations in those reports on those subjects.
Yeah. Okay. Yeah, each does have a long list of references to the impact. So another question, fairly general question on, well, what specific fault characteristics should be used when you're evaluating a storage site?
It's not just simply a question of the fault. You should be, number of points. One is the orientation of the fault, its magnitude particularly in terms of displacement. Is it just going through the reservoir? Is it going through the caprock? Is it extending above that into the overburden? I would say that the stress field acting on the fault and the rock strength of it are particularly important characteristics which need to be taken into account. And a lot of these parameters have to be taken from measurements, say from borehole measurements if you have them, and other adjacent areas where you can measure the, if you like, the regional stress field, so you know the maximum direction of maximum stress and the direction of minimum stress.
Okay. Another question. You talked about capillary seals, but are we any closer to understanding the interfacial tension and contact angles of CO2 within the fault rock brine CO2 systems to predict fault capillary sealing?
There is a paper referred to in the fault permeability study which alludes to capillary action in shales. Now that doesn't directly answer the question, but it does go into factors that affect why migration might occur to some extent through what is normally regarded as a low permeability rock. It doesn't really fully answer the question, but my understanding of capillary pressure is that it's driven by the density of the fluid and the diameter of the pore under which the migration is taking place. So the migration rate is, as far as my thinking is concerned, is that it's governed by, if you like, the fluid property of CO2, or indeed any other fluid, which is one reason why some fluids preferentially migrate across barriers and others don't. But the other point I would make is of course, if you like, the pressure caused by, if you like, the development of the plume. So that migration might not necessarily begin to occur until the plume has reached a certain magnitude in terms of depth in the reservoir, which then induces sufficient capillary pressure to move it across the barrier.
Okay. We'll do two more questions. Time is going by here. Interesting question. In terms of risk assessment, the characterization of fractures over the large sedimentary basins that are needed for large-scale deployment of CO2 storage, will this level of characterization have an impact on the economic costs of CO2 geological storage?
Yeah, that's an interesting question, because a lot will depend. Let's try and constrain this to faults. Obviously, risk assessment has to take account of a number of different factors, and indeed the approach is going to vary depending whether it's on or offshore. As a generalization, offshore storage is going to be a lot more expensive, and therefore the ratio of characterization and risk, well, the monitoring and modeling costs may be proportionately lower on an offshore setting than they are onshore. Of course, it will depend on the geology and the presence and magnitude of faults. So in a case like Sleipner, where you have a large reservoir area, there's very little pressure difference across that reservoir, and therefore characterizing something comparable in terms of faults may not be as high in terms of investment in risk assessment as, say, compared with a site which has, like Snøhvit, which definitely has a fault, or the original reservoir had a fault, and therefore required proportionately more investment. So it's going to be geological, really, site-specific, as to how much investment is going to be required.
Okay. Then the last question, well, it really came in as a comment. It was described as a comment about future research directions in terms of in-situ testing for fault fracture zones and the need for dedicated field test sites in appropriate geological conditions. So I would add to that a question of, are there projects planned or ongoing that are doing or planning to do field tests?
Well, yes, the short answer is it would be a good thing to do, but and particularly where you have good characterization of fault orientation, stress field, and ideally a fluid, preferably CO2, that you can measure. There are, as it happens, the Otway test site are planning to do just such a field experiment or field demonstration of, this is a site in southern Australia which it's a natural reservoir which has a fault running through it, and my understanding is that CO2 or possibly brine, I'm not sure which, there is an attempt to measure its behaviour across a known fault, and that will give you, this will enable the operators to tie in things like stress field, fluid pressure, rate of migration. But the caveat with all of these things is you always have to take account of site-specific conditions.
Okay, but you'd welcome more data.
Absolutely.
From field tests.
Absolutely.
To understand this area, populate the models, etc. Okay. Well, I'm afraid I'm out of time. We're getting a lot of questions still coming in, actually, and they're really good questions. I can reassure you that all of your questions are being recorded, and James will respond to each of those after the webinar. The webinar has been recorded as well, if you would like to listen to it again, and for those who aren't able to listen to it live. With that, I'll draw it to a conclusion. Thank you very much, James, for the presentation, and thanks to our contractors, GNS, and the Norwegian Geotechnical Institute, who did a lot of the underlying work. As James referred to, one of those reports is already published, and the other one we're hoping to publish in the near future on the fault permeability aspects. And then just to end with a thank you for listening, and I hope to see many of you at GHGT in Lausanne conference from the 14th to the 18th of November, where there will be more technical presentations on topics related to fault permeability and its importance to CO2 geological storage. So thank you very much.